Hello, welcome to Pipeline Integrity, things that make me go, This is part two of my video series. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today's topic is corrosion assessment using the NG18 based equations. Some of you will know these equations better as ASME B31G or perhaps DNV F101. If you watched my earlier video number 1, I spent some time talking about why these NG18 based equations are fundamentally overly conservative, and again, spoiler alert, the reason for that is that the NG18 based models are fundamentally mathematically and theoretically wonky. I believe that they're probably costing the oil and gas industry something like $3 to $5 billion per year. Now, if you watch video 1, I promised to show you a solution to this problem, and that's what I'm going to be doing today. But I'm not quite busy on giving NG18 a bruising, so let's see what happens. So here we have our basic NG18 equation. So those of you familiar with this will know it as the ASME B31G or the DNV F101 equations, but pretty much stripped down of the correction factors for shape and such. We have a remaining strength, which is the predicted strength of a corrosion flaw divided by the flow strength of the material. And that's equal to 1 minus d over t, where that's the flaw depth ratio, depth divided by wall thickness, and everything over 1 minus 1 over m d over t. Now that m is the folius factor, which is a function of the length, the diameter, and the wall thickness. If you saw video number 1, I demonstrated that the folius factor is really, strictly speaking, not legitimate for surface flaws. Somehow the whole thing got tied up in the predictions, and quite frankly, I'm surprised that it's really lasted this long in all the pipeline integrity equations. So what we're going to do this time is we're going to look at the limits of this basic NG18 equations and see if the limits match up with our actual industry failure data. So if I consider a very short flaw, the folius factor would be approximately equal to 1. And if you were to use the NG18 equation to calculate the remaining strength, you would find that that ratio of prediction over flow strength would be roughly equal to 1. So essentially you're saying that the predicted failure strength is equal to the flow strength. And that seems logical. Now, if you were to plot your remaining strength against the flaw depth ratio, everything would fall along the red dashed line that you see here, essentially demonstrating that there's no effective flaw depth because it's essentially a zero length flaw. So here I'm just playing with the mathematics, and you'll need to bear with me a little bit. If we consider a long flaw, then the folius factor m gets larger and larger and larger. It will tend towards infinity. Obviously, this is just mathematically hypothetical. And when we put that infinite folius factor into our basic NG18 equation, we find that the remaining strength will tend towards 1 minus dt. So it's actually tending towards the remaining ligament thickness. So that also makes sense. And if we plot that the flaw depth ratio, we'll see that diagonal line. Okay, so we've now considered a short flaw and we've considered a long flaw. And so we would expect that any industry failures would somehow end up between those two red lines. We would expect any actual industry failure data to fall within that predicted zone shown by my pink triangle there. Okay. What I've done is I've dug up some industry failure data. I have two sets. I'll call them the Corona data and the Battelle data. The Corona data comes from a doctoral thesis from the University of Waterloo. There are 40 complete data sets, and those data sets include some full profiles. It's easy to find online if anybody's interested in playing around with math like I am. We also have the Battelle data, which is Pipeline Research Committee of the American Gas Association back in 1974. There are 45 data sets, and these are data sets that would have been used to validate the original NG18 equation almost 50 years ago. So I consider these data sets to be industry credible. Now here I've got all those data points plotted, remaining strength as a function of flaw depth ratio. And as we just saw, it was predicted that all of these data points would be between the red dashed lines, but it seems that they're high. Now, some of these are high because occasionally a pipe test will fail not at the corrosion flaw, but in some other section of the base material. And so we're really looking at a flow strength failure. Some of those are high for that reason. But when you look at the clustering of all of the data, you'll see it's a little bit higher than expected. So this is really consistent with what we talked about in video number 1, where the model is overly conservative. And that's costing somebody a lot of money. Now, some of you might be familiar with my new gamma exponent model. I've nicknamed it the GEM. This is a model I've been working on for the last probably year and a half or 2 years. And what I've done is I've got a remaining strength, so a predicted failure strength divided by flow strength, and that's equal to the remaining ligament thickness to the power of the exponent gamma. And for localized metal loss, that gamma is defined as the minimum of the length over the radius of the pipe, up to a maximum value of 1/2. Now this is a very simplistic equation, and some of you will feel that I just pulled it out of the air as an empirical model, and everything seems very simplistic, and it kind of sort of seemed to work, so I moved on with it. That's not actually the case. There actually is a mathematical derivation behind this. It's a little bit complicated for this video, but you can find it in my journal article that I'll show you later on. Now, some of you will be a little bit surprised about this because the maximum exponent that's used is 1/2 rather than 1, and that's got some significant ramifications. Let's do the same exercise we did with the NG18 equation. If we use the GEM equation on a short flaw, then gamma is going to be approximately equal to 0, and our remaining strength of predicted overflow strength is going to equal 1. So that's exactly like it was for the NG18 equation. The predicted failure strength for a 0-length flaw will be equal to the flow strength of the material. And we plot that in exactly the same way. Again, this is just sort of hypothetical mathematical limits of the equation. Where things get interesting is that if you go for a long flaw of localized corrosion metal loss, the gamma tends to 1/2. And that means that our predicted flow strength, our predicted failure strength over flow strength actually tends to the square root of the remaining ligament. And this is going to cause some of you out there a lot of heartache. Sorry about that. I know that there are probably people thinking of all sorts of nasty words to describe me because this does seem completely and utterly counterintuitive. As I said, I've written a journal article that does have a rationale for this, and let's see how it plays out. Here's our square root relationship, and if we put our data in place, bang. All of these data points, all 85 data points from my 2 industry credible data sets falls within the zone that the GEM model is predicting. So that's kind of an interesting thing. Although we would naturally assume that a longer flaw would approach the remaining ligament solution, it actually approaches the square root of the remaining ligament. Now, those of you that saw video number 1 noticed that the highest of the back calculated folius factors for the data set was about 1.5 or 1.6. And I'll let you know that if you were to plot up the NG18 equation using a folius factor of 1.5 or 1.6, it would very strongly correlate to the square root relationship. The interesting thing here is that we have a gap between the NG18 prediction for long flaws and the GEM prediction for long flaws. And you'll see that there's a big empty zone here. Now, I need to be clear that this is just for my data set. Other people might have data sets that have some outliers that end up in that envelope, but not in this case. That empty area represents over-conservatism by the NG18 based equations. And if you look at the maximum difference there, you'll see that at a flaw depth ratio of about 0.6, you can see that there is about 25% over-conservatism in the NG18 based models. So if you're doing some work on a pipeline that's at full pressure, at licensed pressure, that 25% might correlate to 2,500 kilopascals, or it might correlate to, 350 psi. So if you're the one that's got the checkbook that's basically paying for all the repairs on your pipeline, you're actually giving away quite a lot of pressure. Remember that over-conservatism that I'm talking about here is on top of the typical licensed safety factors of your pipeline, and it's on top of using lower bound yield strength, and it's on top of any tool tolerances that you might add to your calculations. That's a lot of money to be giving away. Now you're probably wondering if the GEM model actually does work. So here what I've done is I've plotted the 85 data points as a validation plot where I look at the predicted failure strength on the y-axis, and I compare that to the true failure strength on the x-axis. You'll see that these data points line up fairly well along the gray dashed line, which would represent ideal conditions. The trend line that I put through these data points comes out with a slope of y equals 0.91x, which means that we're about 10% overly conservative. Now we need to point out here that if you look at the legend, I've mentioned that I'm using an elliptical flaw assumption. So what I do with this is to take the d over t ratio, the corrosion flaw depth ratio with respect to wall thickness, and I multiply that by pi over 4. That's a fairly typical way to do an approximation of a semi-elliptical flaw. So that's what I've done here. Now, when you look at a model like this that has about 10% overly conservatism, you'll see that this is actually a step in the right direction compared to, say, R-string. Studies on R-string show that the model is about 30% overly conservative. And that's not my calculation. That came out of the original Corrosion assessment. And it also came out of a very recent PRCI report. That PRCI report also looked at a modification of R-string, which is called P squared. And P squared shows an overconservatism in the order of 13%. So when you think about it, this simple GEM model, assuming an elliptical flaw, is actually a little bit more accurate than that P squared model. Now, where the P squared model does have an advantage at this point is it has much better precision. Right now with my elliptical flaw, I have a standard deviation on the data set of something around 16 or 17%, and this compares to the P squared model, which is about 8%. Now, in order to try and fix that problem, I've come up with my own level 2 assessment. And what I have done is I've come up with my own little level 2 algorithm, which I call the Hmmm. I'm not going to tell you how that algorithm works. I'm kind of saving that for a rainy day. But I will tell you that when I take the Corrosion data points that did include a full flaw profile and I apply my Hmmm algorithm to it, I managed to improve things quite a bit. Here, the slope of my trend line, y equals 0.98x. That's basically telling me that my model is about 2% overly conservative. But in this case, I've brought down the precision, or I've improved the precision quite a bit. My standard deviation on this data set is about 8%, which puts it comparable with the precision of P squared, or probably a little better than R string. So I feel like that this is an improvement on things, and I need to remind you that these data points have been used assuming that square root relationship. The people that thought that I was crazy 5 slides ago and probably still think I'm crazy should maybe have a think about that and maybe chase down the journal article I've got that explains how and why that happens. If you look at various industry models that are based on NG18, you'll find that there's a long laundry list. ASME B31G, both original and modified, R-string, P squared, API 579, BS 7910, and DNB F101. All of these industry models are going to include some form of the NG18 equation, which includes the folius factor, which I discussed in video 1. And it also predicts that the remaining strengths of long flaws tend to the remaining ligament, but not square rooted. So that should give us something to think about. So if you think about it, the oil and gas industry is valued at about $3 trillion, which puts it at a similar value to the GDP of Britain or France or India. And that's a lot going on. There's something like 2,000 kilometers worth of pipelines in the world, if you consider just the onshore and offshore transmission lines. That's enough to wrap around the world 50 times. If you then add in the laterals, the gathering lines, the various facilities piping, there's an awful lot of piping that's being looked after with the NG18 equation. And the fact that there's such conservatism built into these models, it seems to me that this is costing people an awful lot of money unnecessarily. As one of my former bosses would have said, this situation really seems suboptimal. Now, a lot of videos that you'll find on YouTube will have a disclaimer where they say, this work has been done by a trained professional, don't do this at home, it's dangerous, and various safety cover your tail type comments. You're not going to get that. I'm encouraging you, please do try this at home. I've shown you some equations. I've shown you where you can find the corona data. That's just a simple Google search. You can find that for free. And I encourage you, do try this at home. See if you can plot the data in the same way as I do, or plot your own data in the same ways, and see if you come to the same conclusion that I do. I think those of you that try it will see that I'm actually not a complete crazy person, or at least I hope you find that. If you're interested in this, there's some further reading. I do have 3 publications that I've got out there that explain a little bit more of the theory, so chase those down if you're interested. For those of you that have made it this far, thank you very much for your attention. I hope I've given you a few things to think about. I encourage all of you to play with your own mathematics and see if you can agree with some of my methodology here. Anybody who's interested in this and wants to move on to video number 3, I'm going to be, rather than worrying about corrosion assessments, I'm going to be looking at crack assessments and the log secant models that are used to address cracks. If you've enjoyed this and been entertained by it, I think that you'll find the next videos just as entertaining. Thank you for your time. Bye.